Welcome to Hot Chips 2023. Tutorial 1, ML Inference.
Cool, yeah. So I'm going to be talking about PyTorch 2.0 today and some of the key components behind it. So just an overview, we're going to start by talking about some of the front-end APIs, and then go to three main components, which are TorchDynamo, AOTAutograd, and TorchInductor, and then also talk a little bit about how PyTorch 2 might be relevant for new hardware backends. So just to start, there's two main APIs, torch.compile. So torch.compile will, the goal is to optimize your model without any changes to the source code, and it works by interpreting through the bytecode and producing regions of tensor compute, which we'll call graphs, and ultimately, by default, uses TorchInductor to generate high-performance code. And then torch.export, the goal is to generate one single program for use potentially in non-Python environments that are resource-constrained or otherwise. So torch.compile and torch.export take in your user model code, and then we're going to symbolically interpret Python bytecode, producing like a region of tensor compute, the FX graph, and a residual bytecode, which I'll talk about in a bit, and then through a series of low rings, produce a much cleaner functional graph that we're going to compile. So TorchDynamo, this is the part that interacts with Python bytecode and produces tensor compute. If anyone's familiar with TorchScript, the goal for TorchScript was to compile your entire model, and if there was any failures, it wouldn't work. Similarly, it was capture a single program which would work for all of the variety of inputs. But with torch.compile, if there's something that we don't know how to interpret, we'll just fall back to eager, thereby ending the tensor compute region or graph. If you look at how PyTorch code is written, it's just Python, and so the goal is to work transparently with Python. And if we don't know how to compile something, we just fall back to Python to interpret it. So just an overview on TorchDynamo. We have our original Python function in its original bytecode, and then on the right we have the artifact that's produced by TorchDynamo. So at the top are guards, which are extra checks that we do on the inputs to see that the created tensor graph is valid to be run again when you use a new input. You see the original bytecode has been modified to call FX graph, which is our compiled artifact. And then finally, we have the residual bytecode, which does a couple of things. One, if we had a graph break and we had to file back to Python for some reason, that will be the invocation of the continuation function to fall back to Python. And additionally, there's some mutation or things that we symbolically evaluate, such as a write to a closure cell, which gets generated as an epilogue and then invoked following tensor compute. To evaluate bytecode analysis, we have a corresponding variable for various Python types and tensors and user objects. And you see on the left, you have load global, load adder, load fast. These are Python bytecode that we're symbolically interpreting. And anytime we would interpret bytecode that would interact on tensors, we'll be adding it to a corresponding FX graph so that it can be later invoked at runtime instead of at compile time, obviously. So guards in cache. Guards are a set of conditions such that determine whether or not it's valid to rerun the graph that we created. Compilation unit stores various graphs that we've created, and then if we fail a guard, then we continue next to this the next graph and its corresponding guards, and continue going down that list until we either recompile or we find a reusable program that we've already compiled. So now for an example, this is a pretty simple program where we're calling clamp min, and we're going to take the backward. So the corresponding guards here, we're checking the tensor, and this will do things like check the shape and strides and device, and then we're also checking that it was invoked with an integer in the second input that remains true, and then in this case we've also added a guard that the value is 0 because that's been made into a compile time constant. And the optimized bytecode, instead of like the original Python bytecode, again we're invoking this compiled FX graph. And if you look at the FX graph, just like take a note of it, we're calling the top level Torch API, and so bytecode analysis, when we as it's saying, we have we either add guards to the bytecode, which become compile time constants, or when we encounter a graph break, that gets generated as an epilogue, as well as some other things that we may have to replay, such as mutation that was interpreted during our analysis. So graph breaks make using TorchDynamo much more friendly, because if there's something that's unsupported, whether that's some Python feature or something else that we don't know how to compile, we can just continue, fall back, and then compile again the next function frame invocation. But because of that ease in API use, it also comes with performance costs in that, anytime you graph break, the next time you call again, there's going to be additional sets of guards. And, if there was any important fusions that you wanted to have happen between those two graphs, those no longer happen. So, we have an API like TorchDynamo.explain to look at your Torch.compile invocation and print out guards, and usually that's one of the best ways to improve your performance with Torch.compile is look at the guards and see if there's any easy workarounds or ways to rewrite it. So after TorchDynamo is invoked, we have this next section, AOTAutograd, which was originally written just to lower the forward and backward, but now does a lot more. The kind of normal picture of a compiler for neural networks: it takes in tensors, it produces tensors. But with PyTorch, there's a lot more that can happen. There's like mutation to inputs, or the gradient that we have to, the backward that we have to prepare and save tensors for that. Mutation or producing the backward is very difficult for most compilers. So AOTAutograd exists as a layer above that, so that the final underlying artifact that's compiled to machine code is much simpler. So it will take care of aliasing. It will make it a functional graph, and also lower some of the higher level PyTorch constructs like gradients, or also like automated mixed precision will insert explicit typecasts. And then one other thing I'm not going to get to here is subclasses, where there are another PyTorch 2 feature where you can write a custom way of interpreting PyTorch kernels, like say for quantization or something else. One thing it does is it normalizes the graph, so it removes high-level Torch APIs and replaces them with invocations to the low-level kernels. This makes it a lot easier for handling, complicated PyTorch calling convention, like taking either variadic inputs or tuples, et cetera, et cetera. So it makes it much easier in standardized form post-normalization. So on the top is the typical way that AUTOgrad happens within Torch, and on the bottom in the red is how it works with AOTAutograd. So aliasing is removed. We add guards for the aliasing relationships between tensors. Mutation is removed as well. AUTOgrad is taken care of, and so then finally you just have plain output tensors and the kind of dense compute that compilers know how to deal with. So this is back to our earlier example. This is the first thing that AOTAutograd will do is it will run both the forward and backward into one joint graph, and then partition it. So if you see the where self greater than or equal to min, that's the backward formula, and it's all together in one graph. AOTAutograd will do a partitioning where we may recompute things in the backward or move things from the backward to the forward in order to minimize global memory reads, which makes things faster and in some cases also is a big memory improvement. So that's our original operator, and the original clamp min API has now been lowered to torch.ops.8 down at maximum. So it's gone through a series of decompositions and reducing the operator set. So one thing PyTorch 2 uses is a set of decompositions and primitives, which both take the 2,000 operators that PyTorch normally has and makes them into a much lower operator set. And those decompositions can be opted into per backend if there's like a particular high-level API that's important to keep as one operator. And for reference, I think Inductor has 140 unique lowerings, which is way less than the 2,000 that PyTorch has if you just look at its complete operator set. And it will also do things, PrimTorch and decompositions will also do things like explicit broadcasting and explicit typecasting, which make it easier for a backend to preserve PyTorch's semantics. And like I mentioned earlier, we have functionalization, which instead of this user API x.add underscore, we're going to create a functional form of it. And again, we're guarding on the exact aliasing patterns that it's invoked with. So if aliasing changes and we have to generate a new function, that will happen. And then finally at the end, like a copy under explicit copies back into the inputs are generated for inputs which are mutated. So now to get to TorchInductor, which is our cogen compiler. So some of the principles, it's PyTorch native. So the concepts that exist in PyTorch, whether it's tensors, aliasing, striding, are also represented in TorchInductor. It's Python first. PyTorch gets a lot of user contributions because it's hackable and you can go in and PDB, et cetera, and don't have to build. And TorchInductor is also in Python. And it's breadth first in that it's covering a wide variety of PyTorch operators instead of focusing on a smaller set such that like long tail models work and all of the operators get fused and it works reliably across the many ways that people use PyTorch. So it uses a define by run loop level IR. So we'll get to this later, but it's Python lambdas essentially that capture the semantics of your operator in the same way that PyTorch is a Python code and not a graph structure. works natively with dynamic shapes and strides and uses SymPy to do a lot of symbolic reasoning and simplification. And we use Triton and C++ and OMP for code generations. We're reusing existing technologies that work well. So for those of you that are unfamiliar with Triton, it's a programming language for GPU kernels, and it's often faster than cuBLAS, cuDNN, Cutlass, and it's higher level than CUDA, lower level than pre-existing DSLs, allows non-experts to write fast custom kernels, and OpenAI maintains it, and we're in collaboration with them. So TorchInductor compiler stack, as we already went over, TorchDynamo and AOTAutograd take your high-level Python program and produce a much simpler form, which is then ingested by TorchInductor, and graph lowerings convert operator invocations in the FX form to loop level IR, and we do things like removing views, broadcasting, simplifying indexing. We have a scheduling layer which decides what executes with what fuses, tiling, memory planning, and buffer reuse, and wrapper cogen, which generates a Python function which will invoke all of your kernels and do things like tensor allocation, and then cogen for the actual optimized kernels that we're generating, which is either in Triton or C++. So we're going to go through a TorchInductor example where we're taking sine of the input and then cosine of the intermediary and returning both. I guess one thing to know is we're using TorchDynamo and AOTAutograd, but we could also directly take in an FX graph to do the compilation. Here you see that the high level x.sign has been, the method call has been removed. We're explicitly invoking the operator and its overloads, the particular set of types that it's being invoked with. Each intermediary is has been annotated with both its D-type and the symbolic shapes. So here is the IR. We have two buffers, inner buffer 0 and inner buffer 1, and the functions on the left correspond to how to compute a single element of the output given an index. So we're loading from the input according to the size and the strides of the tensor, forming sine, and then returning it. And on the right, we have the corresponding IR. And as we mentioned earlier, it's a lot of the same abstractions that PyTorch uses. So there's storages, tensors, and layouts. The ranges say how many elements we're going to compute. There's three kind of main IR classes that TorchInductor will handle, which is pointwise, reductions, and scatter operations. So one thing to note about TorchInductor is that we don't try to natively compute like matmul's or congs in our IR, and we have kind of like a separate lowering phase for that. And so we're kind of we do compute heavy operators not through this lowering stage. And then we also have this like global ops variable, so ops.load, ops.sign, and we repurpose that to do analysis on various buffers. So like we globally reassign ops in order to do analysis on memory reads or writes, like value ranges, and then finally cogen, where ops.sign corresponds to Triton .language.sign. And if you were to compose two IR nodes together, you would create a lambda that would call one inner function and then the other. So scheduling and fusion. Scheduling and fusion decides what gets fused with what. Memory planning, re-emplacing of buffers, buffer reuse, and On the left, we have this can fuse function, which determines legality, which includes things like checking for cycles that would be induced, but also in some cases like heuristics on only fusing things that share memory. And we also have the score fusion function, which estimates the amount of memory bandwidth, global memory reads that would be saved by fusing two kernels. So in this case, it's 3 million bytes or something along those lines that we save by fusing the two buffers together. So we kind of greedily generate fusions that are possible, and then rank them by the amount of memory bandwidth we think they'll save, and then we fuse those together. So this is the generated Triton code, and as you see, we're computing. We have a program that's valid for a given block. So Triton, instead of CUDA, you write things in terms of a thread. In Triton, you write programs in terms of a block. And so we load from the input. There's some masking, and we perform sine and cosine, and we then write back to the output. And then this is the generated wrapper code, which is kind of an unrolled interpreter loop, essentially, where we gather the inputs, we do some symbolic shape code in Python, we allocate the tensors, and then finally we invoke the Triton kernel. And then similarly, this is the generated output for the C++ backend, and again, we're reusing OpenMP there. So here are some GPU results. So TorchBench is our collection of models that's supposed to kind of capture the state of the art around various different things people are doing with machine learning, and so it's a wide variety of models. Hugging Face, it's mostly transformer models. And then TIM is a set of vision models that has now also been moved into Hugging Face. And note, we're using mode reduce overhead, which is a PT2 native integration with CUDA graphs, and it includes a lot of nice CUDA graph facilities, such as reusing memory pool across separate invocations, and optimizations around not copying in tensors, which come from the memory pool. So PT2 for hardware backends. There's a number of different extension points that you might tie into. So the first is the pre-grad FX graph, which I wouldn't really recommend because it has implicit in it the mutation and AOTAutograd semantics and unnormalized form, but you could do it. And then there's post AOTAutograd, which at this point, gradients have been handled for you. It's functionalized. And I'll note Onyx has an integration here because I know a lot of hardware backends integrate with Onyx, so that might be a good, easy way just to get initial results or build more thoroughly upon. And then TorchInductor, so we recently added a PR, which I've linked here, for extension points for third party, where you basically, subclass the scheduler and determine profitability of doing fusions and the legality of fusions, as well as generate the final code but you get to take advantage of all of the lowerings we've done in representing A10 operators as pointwise operators, reductions, etc., and indexing simplification. And then finally, Triton, which is the recommended path if it's viable. Intel, XPU, AMD GPUs have both integrated this way and seen good results. And I'll also note that we use Triton to generate matmuls and some other things along the way, like having a Triton template for flash attention, and then because it's in Triton, we can fuse on an epilogue for the other operators that we have cogen for. So this is again the recommended path if it's viable. And then also note that a lot of the things that we use in PT2 are also relevant for PyTorch Eager, in that we have a huge set of decompositions that to make the number of operators you need to implement much more feasible, and also explicitly model type promotion and broadcasting so that you can faithfully execute PyTorch semantics. And also note that we're looking into reusing Triton cogen for eager kernels, which would simplify a lot of things. And then, so if you wrote a compiler backend, you would get eager support through that. That's in the works. There's no specific timeline there. And also note PT2 for non-Python deployment. As I mentioned, torch.export, which will take your PyTorch program and create a single executable graph. We're working on AOTInductor for taking the inductor cogen and exporting it to C++. And there's also this newly released ExecuTorch, which is a runtime targeting edge devices, so very low memory and latency, and optimized for edge compute. So we post a lot on Dev Discuss and updates, PyTorch Slack. If you email me if you want to invite, and then GitHub, raise issues, follow there. Then you're also welcome to email me with any questions. I'm happy to answer questions now if there are any. Okay.
Thanks, Elias. So I think we can start with Slack questions while people line up at the microphones.
Yeah, question from Shabarish Ravikumar by Waymo. Do you envision Inductor to be eventually extended to work on domain-specific accelerators, that is not CPUs or GPUs?
As I mentioned, if a integration with Triton is viable, that's a good way to integrate there. And we have a couple of different backends from A&T and Intel which do that. And then, as I also mentioned, if that's not viable, you can add support to Inductor via our third-party extension APIs, which were recently added. But Triton is recommended, and if not, you can do Inductor.
Thank you.
So we can take one from the person at the left mic.
Hey, I'm Klaus. I have an algorithmic differentiation background, so I'm just a bit irritated. You talk about gradients, and in your example, you had a two-output function. So you have a Jacobian, and then you have your forward and reverse models, but you don't seem to do the Jacobian times vector product itself. You build the full Jacobian every time, and then you lower it via your compiler later on. Or how is that working?
I'm not sure if I fully understood the question, but we generate, we trace out the joint, and then the forward and backward are generated by AOTAutograd. So we ahead of time, as you run your forward, generate the backward that would need to be invoked, as well as decide which tensors need to be saved in order to compute the backward.
All right. We can talk offline after that?
Yeah.
Great.
Yes.
Thank you.
All right, next we on the right-hand side.
It's Pradeep from KLA. Is TorchInductor based on the MLIR framework? If not, why not?
Is it, sorry, say that again?
Is it based on the MLIR framework for progressive lowering for compilation? If not, why not?
Well, Triton is now uses MLIR for cogen, so in a way it is, in that we generate Triton, which then generates MLIR. I guess so we're taking advantage of MLIR that way, but MLIR has a lot of I think one of the arguments for it is different dialects, etc. And I don't know. I guess just it was easier for us first to keep things in terms of PyTorch, then eventually lower.
Got it. Maybe off the microphone, I can hear some interesting anecdotal evidence. Thanks.
All right. Do we have any more questions from Slack? Okay. In that case, let's thank the speaker. All right. So next up, we have Zhibin Xiao giving a talk about hardware support requirements for sparse ML inference. So Zhibin is a co-founder and chief architect at Moffett AI.
Thank you, Tom. I'm the only person between you and the launch. I will finish as fast as I can, and probably can catch up later in the lunchtime. And my tutorial is about hardware support requirements of sparse machine learning inference. So this is the outline of my tutorial. So first, I will introduce the machine learning inference, and then I will introduce the sparsity in machine learning inference, and give an outline of hardware-software co-design considerations for sparsity. And I will also give an overview of case studies in sparsity support in CPU, GPU, and AI chips. So this figure shows a brief history of AI models. This is one of my favorite pictures. I take this from Professor Yong in ISCC 2019, and then I extend this AI model history since 19 to 2023. So there's two actually period of outbreak of computer AI models. The first period, as we all know, it starts from 2012 to 2018, and the 18 to 2023. And the first period is about computer vision. So there's a lot of computer vision models, including AlexNet, ResNet, and for object detection, for classifications, and for segmentations. And for the language model, it all starts from 2018, the BERT and all the transformer models. And then there's a outbreak of GPT model year since November, the ChatGPT language model is so fast, so we cannot actually catch up with this progress. And one of the things I want to mention that for the computer vision and large language model, most of the model operators actually converge to a very small subset of operators. So basically, it's just the matrix multiplication, convolution, vector operations, and scalar operations. And the second thing is the language model become larger and larger, and the training data set become larger. And that's the two observations for the history of this AI model development. So there's another graph here shows the brief history of large language model. It starts from 2018, as we can see in the previous slides, is the BERT model, and 2019 and 2023. So three different companies, organizations are driving force for this breakthrough of large language model. The first is OpenAI, and the second is Google, and third is Meta. And also there's a lot of open source effort to speed up the large language model development. So basically the large language model, they are all based on the transformer architecture. And also there's some different architecture difference. Some is based on the encoder only models, some based on the decoding only models, and some are encoder decoding transformer architecture. For the latest ChatGPT and GPT 3.5, GPT 4, they are all decoding auto generative models. So we are. Until today, every day we read the news. There's a lot of progress in this area, especially in the open source. And like last several days, we are very excited about the Code Llama, which is a Llama 2 version for coding. It's the the performance is great. It's even much better, a little bit better than GPT-4. I think it's really exciting. So let's go into a little bit details on the machine learning inference. So the machine learning model operations actually converge, as I have mentioned previously, is converged to a small subset of operators. So like in the latest Onyx library, it has 192 operators. So it's a very small a set of operators. Also inside these 192 operators, there's some very basic operators like convolution, matrix multiplication, inner product, element-wise addition, mean, reshape. This takes like more than 90% of number of parameters and also computation flops. So as this, the two figures shows two very typical models in computer vision and the language model. The left is ResNet 15, as we can see. So the ResNet 50 actually it becomes a very simple model. It has 50 layers, but the operators is mainly convolution, matrix multiplication, pooling, and loop. And on the right side is a transformer model, and the operators are basically just matrix multiplications, element-wise operations, JALU, softmax, embedding lookup. So it's not that complicated for the machine learning inference. So next, I will introduce a little bit on the sparsity in machine learning inference. So as we all know, the core of machine learning inference is a tensor algebra. So basically, you operate on different dimensions of tensors. As we can see here, we have different dimensions of tensors. There's 1D, 2D, 3D, 4D, and 5D tensors. And all these tensors are organized in some format, for example, in a NHWC format in image processing. So sparsity actually in these tensors actually naturally exists, or we can induce by pruning or some different techniques. And the sparsity is a very nice feature to have because we don't have to store the zeros. And also we don't have to compute zeros in a tensor. So it has a lot of benefits, including save storage, save computation overclock time, and reduce the memory bandwidth and capacity requirement, and also reduce power. But it all comes with overhead. So this is called sparsity tax. So to support sparsity, there's extra hardware for compression, decompression, schedule, and also for the computation overhead. So this makes sparsity support very hard. So everybody talking about sparsity, but not all the AI accelerators actually has the sparsity support that can speed up the applications or models in overclock time. So previous slide talked about sparsity for tensor, and then for the convolution kernels, the sparsity is the same because we all know the convolution can be converted to matrix multiplication, matrix weight matrix. As we can see here, there's 3 different levels of sparsity for weight matrix. So if we have a weight matrix with image to column operations, we can convert to a weight matrix here. And there's 3 levels of sparsity. There's a failed sparsity. If there's a failed sparsity, means the whole kernel is pruned off, and then the whole low of this weight matrix is 0. And there's also a shape sparsity. Basically, for each of the kernels, some of the position in this kernel shape, this can be pruned. And then this means some of the column of the weight matrix can be reduced or get rid of. And then there's a channel sparsity for convolution that after the image to column, the bunch of columns in the weight matrix can be reduced, can be get rid of. And there's three different sparsity for convolution kernels. So it all ends up the sparsity for matrix multiplication. So this slide shows sparsity in the research area. So sparsity is an active algorithm research area. So as we can see here on the left is a photo I taken from the very great paper from Dr. Hofer on the overview of the sparsity in deep learning. It shows there's a lot of research is being done in the model specification, both in inference, in training, and in hardware accelerators. And also there's a software acceleration for sparsity as well. So on the right side, it is a paper from Google DeepMind called Fast Sparse Curve Nets. And this is a very, I think this is a very interesting photos here, figures here. This shows the sparse efficient nets versus efficient nets. So if we keep the accuracy as a constant, so the sparsity efficient nets can have much less computation flops compared to the dense efficient nets. And if we keep the flops as a constant, as we can see here, the sparse efficient nets can achieve much higher accuracy than the dense efficient nets. So this actually shows a very good results for the sparse neural network that it can reduce the computation under the same constraint of accuracy. It also can increase the accuracy under the same constraint of the computation power. And So there's another paper in 2019 that's ICLR, the best paper, is a lottery ticket hypothesis paper. This is a very important paper because it demonstrates that any dense neural network, actually you can find one sparse neural network, which is equivalent or comparable to the dense network. So let's go into a little bit deeper in the type of sparsity in machine learning inference. So there's as we can see here, the operation here is a sparse weight or activation matrix, and there's a sparse activation matrix. Then there's the output. So based on the type of sparsity, there's a static sparsity or dynamic sparsity. And inside this category, we have a weight sparsity. So weight sparsity, it can be static weight sparsity. So basically, you prune the weight before the runtime, and this is then during the deploy time, you have a sparse neural network that cannot be changed at runtime. This is called static weight sparsity. But there's also dynamic weight sparsity. So this is a conditional sparsity. So basically, you have a very large neural network, but based on the input, you do a little bit of calculations, and then you use that calculation to select which part of your neural network to activate. So this is called a conditional dynamic weight sparsity. And also there's activation sparsity, which is, we all know there's an input, there's an activation feature map. For large language model, there's activation sparsity for contextual sparsity. Contextual sparsity basically means that for a series of input sequence, the attention can be sparse. So basically, you don't have to calculate the correlations between different tokens in a long sequence. So this is called attention sparsity. And also for the computer vision application, there's a feature sparsity. So basically, in an image input, so if you have an object, and other than that object, the other part of the matrix or input can be ignored. And this is two different type of sparsity: static, dynamic, weight, and activation. And also based on the granularity of sparsity, there's coarse granular sparsity. Basically, you have a very coarse. You can have a like, subset of neural network, or a very large block of neural networks can be pruned. This is called a coarse grained sparsity. You can also have fine grained sparsity. For example, for convolution, you can prune in the channel wise. And also for the sparse pattern, there's a structured sparse pattern sparsity, and there's unstructured sparsity. So I think the sparsity matrix storage format is one of the most important things to consider before we even consider to design a sparse AI accelerators. So this is a very actually this is a very nice figure here, shows that for different kind of sparsity level, the best or the most storage efficient way to compress or to store the weight matrix. As we can see here, there's a dense matrix, there's a low sparsity matrix, medium sparsity matrix, moderate, high sparsity, and extreme sparsity matrix. And to compress this matrix, there's different ways to compress this. If there's no sparsity, then we always store the dense matrix. And if there's a very low sparsity, and the most efficient way is use a bitmap, like to indicate the 0 or 1s in some positions of your matrix. And there's a bitmap. And then there's a long length or delta encoding for some medium sparsity weight matrix. And then there's for the moderate or high sparsity, there's a compressed sparse low or compressed sparse column encoding format that I will explain a little bit further in my next slides. And also there's a coordinate offset kind of encoding format for very high sparsity level, which use the index value pair to encoding the non-zero values inside a weight matrix. And also there's people combine everything together. There's a hierarchy hybrid sparse format to combine this together, so you can make it most efficient for your application. Okay, so previous slides we introduced for different sparsity level, we have different encoding format. And this slide shows the sparse matrix format, which is the most popular format, CSR and CSC format for the sparse matrix. Let's go into a little bit deeper into how it works. It's not that complex, it's very simple. So for the CSR format, as you can see here, we have a sparse matrix. We have a sparse matrix, and we have it's a 4x4 matrix. And if you want to encode this in a CSR format, then we have three different arrays. And the first array is the low pointer. The second array is column offset. The third array is the data. So the data, as we can see here, the data stores all the non-zero values for the whole matrix. So here we can see A, B, C, D, E, F, G. We have 7 non-zero values. So data array store all those. And then we have a column offset, and the column offset records the actual column index of the data. So as we can see here, A, the column is 0, so it's a 0. B, the column is 2, and it's 2. And C, the column is 3, so it's a 3. So basically, the column offset for CSR has the same dimension as the data array. So, so we don't compress the column or data, but we compress the low. So the low is the low pointer is compressed because for this low pointer, in each of the element of this array, it records the number of non-zeros of previous I-1 loads. So as we can see here, for this low A, and there's only one, there's 0 non-zero values, so this is 0. And then for this low D, and there's one, for this low D, there's 3 non-zero values, so we record the value 3 here. And for this low, there's 1, 2, 3, 4, 4 different 0 values. And we put a 4 here. And then here, there's 6 0 values. in previous law. So we put the 6 here. So for the CSC is similar. So you just compress the column. So it's the same. It's very similar. So this two is two most popular formats for compressed weight matrix. And there's another way to compress the weight matrix is called coordinate index or index value pair, and this slide shows this index format and also the hierarchy hybrid format. So as we can see here, this slide also shows the structure and the unstructured sparsity. As we can see here, the structure sparsity, if you compress in the R dimension, just one dimension, so you prune one row of this matrix. And then this is very structured. And the pruning rate is very low, means that we cannot compress the weight matrix without sacrifice too much of the accuracy. So, and in the middle, there's a block-based rate. So the index is inside is a 4x4 kind of index array. So it is a block-based. So it has medium like prune rate. And for the unstructured sparsity, basically you can, the non-zero values is spread over the matrix unstructured. It can have very high efficiency or accuracy with the same sparsity ratio. And then the index range is a 8x8 array. But for the unstructured sparsity, there's a sparsity text, as I mentioned before. On the structured sparsity, the decoding parallelism is very high. And also for the unstructured sparsity, is very difficult to decode in a very highly parallel way. And so basically, there's a trade-off between accuracy and decoding speed for this kind of block level sparsity. And also, there's a hybrid format that we can actually, like this, we have a 2x2 kind of block, and inside this 2x2, this whole block is 0. And then inside this another 2 4x4 matrix, we can use a CSR, CSC, or index value pair to encode this matrix. So and there's a more design on hierarchy hybrid format. Okay, so previous two slides I talked about weight matrix, and this is activation sparsity and conditional sparsity. So it is a little bit detailed on the activation sparsity. As we can see here, the ReLU or the softmax, they can actually induce the sparsity inside the activation matrix. And it's dynamic in nature because it's data dependent. It's generated, the sparsity is generated at runtime. And also there's a conditional sparsity, as I mentioned before. The conditions are calculated at runtime based on the input, and use those conditions to decide which part of the network to activate. And this is a very famous MOE kind of mixture of experts. A network for scaling large language model. They are using conditional sparsity. We can call it conditional sparsity. And as we can see here, there's input, and then we have a router, and the router normally use a top K algorithm to select which network to activate. And also we can have a weighted sum of those active network to generate the final output. And on the right side, there's a sparse attention, and the sparse attention is based on the sequence. Yeah, I think I have very limited time, so I will have to speed up a little bit. So as we can talk, as I have talked about, there's a sparse text for support sparsity. So there's actually 3 different type of hardware device we have is CPU, GPU, and AI accelerators. So the normally CPU, we use those for the highly sparse matrix vector sparse operations in the HPC field. And for the GPU, the recent GPU like Ampere and Hopper from NVIDIA, they have a fine-grained 2x4 structure sparsity. And for the AI accelerator, we can actually design different accelerators support the very complex, different format of sparsity type, but it all depends on the hardware tax we want to pay. And when we design a sparse accelerator, this is a general, kind of very general, high-level picture of an AI accelerator. So basically, you have a graph, you have a scheduler, and you have a bunch of tensor cores, and you have a memory system, and you have an interconnection for scaling out the architecture. So the sparsity has impact on all of these design parameters. So it can affect the programming model, but not too much. It can affect the data flow and the scheduler because the sparsity change the dynamic change the behavior of the workload. So the computation and the memory requirement is different. And the data flow or schedule of those scheduler of the data accelerator has to change. And the sparsity design has a major impact on two components, is the memory system and also the tensor core data path. So this triangle shows the design trade-offs for designing sparse accelerators. So the architecture design is all about trade-off. So before we trade off about performance at the hardware cost. But here, when we're considering sparsity accelerator design, we have to trade off. There's another level, is model accuracy. So it adds another level of complexity to the architecture design for sparse AI accelerators. So the model accuracy we consider about the architecture and algorithm co-design. It may have different application requirement. Maybe some applications can sacrifice some accuracy, thinking you can use a very aggressive sparsity or pruning mechanism. And also it depends on the cost to retrain, because some of the pruning algorithm is pre-chain, and some of them are post-chain. But it all depends the customer's requirement to cost to retrain. And also it depends on the time to market, whether the specification adds too much time for people to deploy models in the real applications. And also the benefits is very clear. As we can see, there's a wall clock speed up, there's power savings, the area savings, and all come up, all reduced to a TCO savings. And then the sparsity tax, as we talked about before, is a decompression, compression, and also there's a sparsity creates another problem for the workload. So there will be a workload imbalance. So even you have a very large number of tensor cores, but if you don't design the sparsity pattern well, then you have very low utilization ratio. So this creates workload imbalance problems. And also, also all the sparsity support requires extra area, extra power, and this is all design trade-off parameters. Okay, I think the next I will showcase some of the case studies in the sparsity support in CPU, GPU, and AI chips. So this slide shows an overview of the mainstream AI accelerator architecture. So as we can see here, there's a popular AI accelerators, and there's a special AI accelerators based on very special technology. So the popular AI accelerators is based on the TS, traditional digital or FinFET CMOS technology. As we can see here, there's a CPU, x86, RISC-V. They're all adding, thinking about adding sparsity for the vector or matrix instruction extensions. And then there's a NVIDIA Tensor Core. It's based on a 4x4 gen, and also they already have the 2 out of 4 sparsity. And for the Huawei Ascent, the P element is a little bit larger, is 16 by 16, and is a matrix multiplication with a vector processor kind of combination architecture. They don't support sparsity. For the Google TPU, is a systematic array plus VPU architecture, vector processing unit architecture. They don't have sparsity. GraphCore is a massively parallel BSP cores. They don't support a fine-grained sparsity, but they probably can support the coarse-grained sparsity. And the Sambanova has a data flow RDU reconfigurable data the flow unit kind of architecture. They support some sort of sparsity. I will introduce a little bit later. And the Cerebras, the wafer scale mining core architecture, they support very fine-grained unstructured sparsity. The Habana Labs and the Intel is based on the DSP array and the GEM unit, and they don't have support of sparsity. And there's other like DSA accelerators like Cambrican, Hanguang 800 from Alibaba, NVDA, and the Tesla FSD. They don't support sparsity, but they are DSA accelerators. And for the other type of accelerators, they based on like spiky neural network, neuromorphic architectures, or memristor, or analog computing, and optical computing. So this special technology accelerators is very efficient for certain applications, but it will have very limited operator support. So next we'll go through some of the sparsity support in different architecture. For example, to support the sparsity in CPU offers a thread level and a very dense vector matrix instruction extensions. And there's a company called Neuromagic. They actually have some commercial products for sparse accelerators in the specify AI models in CPU, and it has a limited sparse speed up, and also the CPU is not very good for those matrix multiplication, compression, and decompression for the sparsity format. And there's some sparsity support on the GPU in the research area, like 2019 Micron paper. They propose a vector-wise the sparsity matrix encoding. So basically, a sparse matrix can be encoded as a non-zero data value and the index kind of offset array, and then they multiply the sparse matrix with a dense matrix. And it has a very minimal change. At that time, they want to add this extension to Volta GPU. And it shows 75% sparsity with 1.49 speed up. And this is academic research. And in 2020, actually, NVIDIA followed this pattern. And then they introduced 2x4 kind of fine-grained structure sparsity support. And as we can see here, it just limited the size of the bank to 4. So inside, if we have a dense matrix and then we have a fine-grained structure sparsity, basically inside each 2x2 small matrix, and then you enforce their 2 non-zeros and 2 zeros, and then you compress this sparse format to a non-zero data array and a non-zero index array, and then so this is a little bit microarchitecture here. So basically you use the index to select the input activations and then do the dot product operations. And the idea is very simple, and the result from NVIDIA shows very good speed up. As we can see here, they show the performance speed up on matrix applications, on the convolutions, and on real applications. So on real application, they show around 1.3 times the speed up. And for the matrix application and the convolution, they show around 1.5 to 1.7, even 1.85 kind of x speed up with 2x sparsity. And this is all the data from NVIDIA website. And for the TPU support, there's no commercial TPU support for sparsity, but there's academic research on support sparsity in TPU. But TPU is very difficult to support sparsity because it's very static and a fixed data flow. But there's some research in published in 2020. They propose, as we can see here, if we have a sparse matrix, if we map to the tensor, the systolic array, then there will be a lot of like empty slots in the array. But they kind of decompose this sparse matrix to multiple packed sparse matrix. And this inside each of the packed sparse matrix, they mapped to one row of the systolic array. So in that case, that the empty slot in the tensor in the systolic array is reduced compared to this the original sparse systolic array. So they show very good result on this, but since this is academic research, it's not verified in the chip. And they have some kind of complicated ALU design to support. You want to latch the input, bypass the input, or do the accumulation operations inside the CPU. And then there's a come up with MIT Aries project. There's Aries V1 and Aries V2. They all support kind of sparsity. And this is I think I don't have too much time, but I will quickly go through this. It's an MIT project. They are Aries V1 and V2. And V1, they support static weight sparsity, only compress the weight on the memory inside the memory, but they don't save the memory, the wall clock. And then they use a long length kind of coding for weight sparsity. And it can do zero skipping for power saving. And Aries V2 is another project. They extend this to a more scalable design to support dual sparsity, and it can have a wall clock speed up actually in 2018. And they changed the compression format from the long length to CSC kind of compression format. And the EIE is a paper from Dr. Han Song, MIT, is in 2016. They actually support a dual sparsity, and the weight matrix is encoded in CSC format. And also they propose a way kind of activation buffer queue to solve the workload imbalance problems. If you are interested, this is a very early paper on this, and it's a very pioneer on the compressed deep neural network sparse AI accelerator design. The microarchitecture I'm not going to go over. And there's some commercial one which supports sparsity is Alibaba Hanguang 800. It supported it's like Aries V1. It supports the sparsity format inside the memory, so it can reduce memory bandwidth, but it doesn't speed up the wall clock. So it's a DSA architecture. So it has a sparsity engine to pack and unpack the weight. And another commercial example is Semanova. Semanova supports sparsity, and then they support a CSR-like matrix compression. And if you are interested, you can go to 2021 Hot Chips, and they have some explanations on this. And they increase they can have wall clock speed up. And Cerebras is another example, and in 2022, last year, they can support unstructured sparsity with a 10x sparsity utilization compared to GPU. And it's not clear on the weight sparsity storage format. I think they probably use kind of zero detection logic without compressed weight inside the memory. That's my guess. And also, there's two recent changes on sparsity transformers. One example is from the Neural Logic, the company doing the software sparsity acceleration, and then they have very good result on 2x sparsity speed up on GPU for the OPT 175 billion models. You can check their website for some of the details. And the Cerebras also, they propose some kind of sparse GPT transformers to run on their Cerebras architecture. So here come to a summary. So sparsity is a very active research area, and it's have a lot of benefits to save memory bandwidth, capacity, and computation time. But the memory, in considering the architectural design, it adds another like model accuracy design parameter to the trade-off of the architecture. And the memory storage format is the key for hardware support of sparsity. So on Tuesday, I'm going to give another presentation on Moffett Deep Sparse AI inference chip. And if you are interested, you please come to our session. Thank you.
Question from Cliff Young, Google. It starts with a comment that he thinks the deep learning sparsity has been pretty dense so far, maybe reaching 10% non-zeros. But on the other side, high-performance computing sparsity is much better, perhaps 10 to the power minus 4, 10 to the power minus 5 non-zeros. Beyond just hardware support for mild sparsity, what do you think are the most promising directions for improving neural network sparsity through algorithmic changes?
So the last part, can you repeat
So
that?
beyond just hardware support for mild sparsity, what do you think are the most promising directions for improving neural network sparsity through algorithmic changes?
Yeah, I think that's a good question because in our design, actually we require the algorithm to prune the model in some certain way. So the algorithm has to change based on the hardware kind of design complexity. And actually we found that algorithm change is actually very, they can accommodate to the hardware complexity. So they can actually prune the model based on the requirement of the hardware. So yeah, I think also answer another question is from the dense to very sparse. There's a lot of trade-offs. So you have to design the accelerator to target certain applications, and then you have to prove from the algorithm level. Then you start design your accelerator. Yeah.
Okay, thank you.
Hi, I was thinking about how sparsity relates to computational efficiency. And I think you have to be careful here because, what we heard today, and this is a common knowledge to all hardware engineers, is that computation is cheap, data movement is expensive. And although sparsity, of course, decreases the size of your inputs to your operation, it decreases the number of operations more. So could you comment on how sparsity affects computational intensity or operational intensity, and what that means for the effect of sparsity on efficient computation?
Okay, I think that's the question. It's all regarding about the sparsity tax we want to pay, right? So I think it's really depends on the, as I already mentioned in my slides, it all depends on the application requirement and starts from there. So you can design some sort of sparsity level. And after that, you need to choose the right way to implement the sparsity because the different format or different memory system has different efficiency. So that's why in my organization or in my talk, we introduce a very comprehensive end-to-end architecture simulator. So we inject the hardware overhead sparsity level as well as some of the compiler optimization in the architecture simulator. So we have very comprehensive simulation before we actually design the chip. Yeah, because the chip is very expensive.
Maybe I could talk to you offline because I don't want to debate in this form, but thanks.
Sure, thank you.
Yeah, this one is again from Cliff Young, Google. And it relates to the sparsity tax. So the overhead of extra operations on top of each neural network multiply accumulate seems to be the key. So can we get more quantitative about the sparsity tax? So for example, there is this out of order tax, which is around 2 to 4x. So what do you think is the numerical value of the sparsity tax? Of the neural network sparsity tax will be?
Yeah, actually, that's a very good question. I think using the architecture simulator, we can determine some sort of like hardware overhead for that. But it's all it all depends on the sparsity level, depends on the your size of your array or your computation tops of your array, and it is because the percentage of your hardware overhead can change, right? For large chips, you have more area to spend. So this is there's no exact number, but we do need a very comprehensive method to simulate for architecture simulation or explorations. Yeah, thank you.